In this video, we discuss the algorithm steps of AdaBoost, which is characterized by resampling the training samples by reweighting. Briefly, the steps are shown in this pseudocode. It is actually not pseudocode. This is just a mathematical description of the steps. The algorithm will reweight the training samples and train weak or base classifiers and give the classifiers, the trained predictors, a weight. Finally, it combines all the learned weak classifiers to form an ensemble. So let's have some detailed discussion about the steps. The first step, I haven't distinguished the two concepts, but they are linked together, but they're different. We can understand the step by either to let a classifier to be trained on the training samples with a weight associated at each sample. So we can see that previously, when we have make mistakes at some sample like x1, remember this funny symbol? That means if the condition is true, it returns 1, otherwise it returns 0. Previously, all the samples are equal. But in the boosting algorithm, some samples are more equal than the others. Well, this is just a metaphor. Some samples are weighted more than the others. And how they are weighted, we will see later in the algorithm. But what I want to say to address the confusion is, here we do not necessarily need to perform the weighted optimization, weighted training for the base classifiers. We can actually do random resampling of the training samples by using the weights of the individual samples. And then in the resampled set of training samples, this is a bootstrap sample with reweighting. We perform the training as the standard steps. We don't employ any more weights because the weights has been considered during the random sampling process. This way will significantly simplify the training process with statistically same effect as what is designed in the algorithm. So this explains the error mirrors. I have mentioned that this means when there is an error, it returns 1, and this return error is weighted by the sample weights. Okay. After we have get the selected weak classifier, the selected base predictor on the reweighted sample, we need to weight these predictors according to its performance on the sample set it has been trained on. So the hypothesis weight is calculated according to the performance as follows. In the formulation, the equation is as presented here. Let's have some explanation. The epsilon star t represent the errors that has been made by the predictor that has been learned in step t, and the star represents the learned predictor. As we have seen in the learning framework, the returned hypothesis, the best hypothesis, the selected hypothesis is denoted using a star. When the error is large, then one means the error is small, the nominator is small, and the denominator is large. So the result of this factor is small. This ratio is small. So alpha t is going down. That means the weight is lower. On the other hand, when the error is small, so the correctness, the accuracy, 1 minus error is large, and the ratio goes up and the weight goes up as well. Drawn curve, it is like this. So this is the error rate. When the error rate is large, the weight is very small. When the error rate is goes down, the weight goes up. In practice, the weights are always above 0. They does not go below 0. Why? That is because we are now consider a binary classification problem. A classifier cannot go worse than half, which is a random guess. Remember, in previous discussion we have said, for ensemble to work, a basic condition for the base classifiers is that they work a little bit better, at least is as random guess. If it is worse than random guess, we can just flip its decision. After we have calculated the weights, we can update the sample weights in the next round of training. The update is go like that. Whenever we meet errors at a training sample, note the size of the font I've used, we make its weights go larger so that in the next step it gets more emphasized. If we do correct prediction at a sample, we will reduce its weights. We do not care too much on this sample anymore because we have already been able to predict it correctly. And this reweighting is modulated, is adjusted by the amount of the predictor's weight. Because if you have a very accurate predictor, we would say that if a good predictor cannot predict some sample, that means this sample is really challenging. We need to adjust its weight by a large amount. On the other hand, if a reliable predictor says this is easy, you can reduce its weight, the sample's weight by a large amount. On the other hand, if the predictor is a bad one, is a poor one, does not work too much different from random guess, we don't listen to this predictor too much, and we don't change our sample's weight too much according to the performance on that predictor. After all, we need to normalize all weights so that they become a probabilistic distribution on the training samples. Therefore, in the next round, we will be able to resample the samples. So, in this as the mathematical explanation of the algorithm. Here is a pseudocode of AdaBoost. If you want to implement the algorithm, you can follow the steps here.